Hi everyone. In the last lecture, we generated a MOSFET structure. Today, we calculate its input characteristics. Since the gate terminal is regarded as the input terminal, the term input characteristics simply means the ID versus VG relation. Since we are performing the drift diffusion simulation, a set of coupled equations should be made. As discussed before, we must include the Poisson equation, two continuity equations, and the contact equation. For each lumped element, we need its own equation. Finally, for circuit nodes, the KCL is applied. Also, by setting up book, we can monitor the gate and drain terminal quantities. In this example, the output file is input_iv.csv. Of course, you can add more quantities of your interest. Although we wanted to increase the gate voltage with a zero drain voltage, the drain current is also zero. We need a non-zero drain voltage. Usually, we consider two cases. In one case, a small voltage is applied, for example, 50 millivolt, 10 millivolt, or 1 millivolt. In the other case, VDD is applied. In this example, the drain voltage is directly increased to 0.05 volt with an initial step of 1.0. It is possible because 0.05 volt is not that high. After learning this solve statement, we have a solution at Vg equal to 0 volt and Vd equal to 0.05 volt. Of course, when the target drain voltage is VDD, it would be difficult to get the solution directly. In such cases, you can arrive at the target drain voltage by adjusting these parameters. Now, we can increase the gate voltage from 0 volt to 1.2 volt. This figure shows the result obtained without considering any physical model. The electromobility is constant. It is clearly seen that the drain current beyond the threshold voltage is linear when VDD equal to 0.05 volt. When you recall the drain current in the long channel limit, it is easily understood. The threshold voltage can be estimated by finding out an intercept point of the tangent line. When the drain voltage is 1.2 volt beyond the threshold voltage, the MOSFET is operated in the saturation mode. You can easily find a parabolic behavior of the drain current. This figure shows the same data in the semi-logarithmic scale. For this graph, you should be able to estimate the subthreshold slope, the dibble, the on current, and the off current. The subthreshold slope is worse than the ideal value of 60 millivolt per decade. It is because we have a highly doped substrate. The dibble is almost negligible because we have a long channel device. I1 is the drain current at Vg equal to Vd equal to Vdd. It is almost 1000 microampere per micrometer in this graph. However, it is highly overestimated. I of is about 1 picoampere per micrometer. Note that the previous results were obtained without any physical model. The electron mobility is constant, and the SRH recombination model is neglected. So now let's consider those models. By adding these lines, we can consider the inversion layer mobility and the velocity saturation. Also, the SRH recombination is included with its default parameters. The mobility model may reduce the drain current. The SRH recombination may increase the leakage current. The blue lines in this slide are the result with physical models. Compared with previous brown lines, the reduction of the drain current is clearly observed. So then, what is the actual on current of this device? It is about 120 microampere per micrometer. Therefore, it is really mandatory to consider appropriate mobility models when you simulate the MOSFET. Another observation can be made for VD equal to 0.05 volt. Beyond the subthreshold voltage, the previous brown line was perfectly linear. But now, with the mobility model, the blue curve is not linear anymore, even beyond the threshold voltage. It is because of the strong dependence of the electron mobility on the vertical electric field. The velocity saturation does not play an important role in a long channel device. When we draw it in the semi-logarithmic scale, the reduction of the drain current becomes even more clear. On the other hand, we cannot observe significant increase of the leakage current. Yes, in this case, the SRH recombination does not play a significant role, mainly due to the model parameters. That's it for this lecture 11. We have studied the input characteristics of a long channel MOSFET. Since the gate length is long, there is no dibble. Also, the velocity saturation is not important. Only the inversion layer mobility is an important physical model. Of course, it is only valid for a long channel device. In the next lecture, we will study the output characteristics of this MOSFET. After that, we will reduce the gate length. Then, short channel effects will occur and things become much more interesting. Thank you and see you later.